So this is Engineering Statistics and Linear Algebra 18 EC 44, Module 2, Lecture 4, Multiple Random Variables. In the Lecture 4, we are dealing with the Gaussian bivariate random variable. So from here, examples will start. Some of the examples will start, and then we'll take the independence and such issues in the next lectures. Okay. So in the Gaussian bivariate random variable, we have seen the what you call single random variable, how the Gaussian random variable looks like. The PDF for the Gaussian random variable looks like. Now we will consider the same thing over here. We just extend it to the two dimensions or two different random variables Z1, Z2 together, and then it will become a Z1, Z2 plane, and hence corresponding to that, we will get the normalized Gaussian bivariate PDF, which is defined to be something like this: f Z1, Z2, Z1 comma Z2 equal to 1 by 2 pi root of 1 by sigma Z square. The exponential of minus Z1 square minus 2 sigma Z, the rho Z, Z1, Z2 plus Z2 square multiplied by 1 by 2 into 1 minus rho Z square. Now this rho Z magnitude should be lesser than 1, and the root of 1 minus rho Z square should be greater than 0, because this is less than 1, this should be greater than 0. So we will go through a detailed study of whatever we have studied written over here, and check whether all the requirements of the bivariate PDF are satisfied or not, and is it a reasonable extension of the Gaussian single random variable. So if you inspect the 3.63, then we should remember that because this is a PDF, the PDF has a property that should always be greater than 0 between the limits minus infinity to infinity of Z1, Z2. So 3.10 should be satisfied, and 3.10 should be straight away concerned with this. So we can just go through that and see what is 3.10. I think it is whatever we have written there. So this is 3.10, same thing, xy greater than 0. So in place of xy, we have Z1, Z2. That's all. So, okay, Z1, Z2 greater than 0. So now the equation 3.17 indicates how to obtain the PDF Z1 for a single variable from a two variable case, and that will be f of Z1 equal to minus infinity. We want Z1, therefore we should integrate it with respect to Z2. Okay, if you integrate the PDF of the multiple or bivariate random variables with respect to Z2, we'll get the PDF for the random variable Z1. So if the technique of completing the square is used in 3.63, that means you need to substitute that and put it properly. That means you can write this, whatever is there over here, from the equation which is written from here, and then if you want to write this total thing in the form of the square, right, in the form of the square term, okay, this thing is to be written in the form of square, okay, then we will get, that is what is the completing the square. Then the PDF can be written as f of Z1 equal to e to the power of minus Z1 squared by 2 divided by 2 pi root of 1 minus rho Z squared integral minus infinity exponential of minus Z2 minus rho Z1 squared by 2 into 1 minus rho Z squared. So this you will get it if you apply the change of the completing the square. Completing the square means writing whatever was there over here in this thing in the form of square, right? We have Z1 square and Z2 square. We should be able to write in the form of square. So that means, we should have minus Z1, for this you can try to write the quantity which will give you the square of Z1 something, and then Z2 Z1 minus Z2 something with coefficients, and Z2 separately with again some coefficient. Okay, so you can write all that. The following change of variable is introduced, that is u is equal to change of variable is z2, uh, rho z z1 divided by 1 minus rho z squared. So if you do that, you will get the value of f of z z1 is equal to this quantity. In the same way, we can get the f of z2 z2 is equal to 1 by 2 pi root of minus z2 squared by 2. Now, from this, that is from the 2.23, let us see what is 2.23. So 2.23 is this, f of z of infinity is equal to this, right? So looking at that and the PDFs 3.65 and 66, we will get this quantity is equal to integral of f of z1, z1. That means we have already written here. So if you integrate once more with respect to z1 both sides, then we will get whatever we want, double integral of the PDF of the multiple random variable or bivariate random variable, right? So, and that is equal to this, that is what is specified here, that is integrating both sides of the equation which we have written over here is what we have written here, and similarly it is equal to this, and that will be equal to 1. Therefore, 3.12 is satisfied. 3.12 is what we have written again, double integral, that is double integral of the PDF is equal to 1. Okay, integral of the PDF should be equal to 1. Double integral if it is a two variable. Equation 3.67 completes all that we need to do to verify that 3.63 is a bivariate PDF. So that is, this is a condition that this is a bivariate PDF. So the PDFs in 3.65 and 66 tie the definition 3.63 to the Gaussian random variable, and also that 2.54 and 55 we have the mean and the variance of the random variables z1 and z2. So we have the mean of z1 and mean of z2 in case of a Gaussian random variable to be equal to 0, and the variance of z1 and z2 is correspondingly sigma z square equal to 1. So these are standard values. Mean is 0 and standard deviation is 1 for that case. So let us see the correlation in the same way. So correlation is E of z1 z2 integral double integral z1 z2 f of z1 z2 z1 z2 dz1 dz. So again, you can apply the squares formula, separate them, and try to solve that, and that will just give us the whole thing, which is something like this, and that will be the value which is rho z. E of z1 z2 is equal to rho of z. So this will be the final equation. So therefore, the parameter rho z appears in 3.63 in the correlation of the normalized Gaussian bivariate random variable z1, z2. Actually, we note that the correlation coefficient, and the covariance are equal in this case. The correlation coefficient, and the covariance are. So this is covariance. This is the what you call correlation. This is the correlation coefficient. All of them are equal, okay, in this particular case. So general Gaussian bivariate random variable. Earlier we took the mean equal to 0. Now we'll take the general. The results presented thus far only for the normalized case. Normalized will have the Gaussian bivariate random variable z1, z2 will have mean 0 and variance 1. That is normalized. But if you take the general one, okay, so again, for a normalized one, the correlation coefficient is written as rho z. However, these results are easily extended to a more general Gaussian bivariate random variable x1, x2, where x1 is sigma x1 z1 plus mu x1, and x2 is sigma x2 z2 plus mu x2. So again, this becomes a linear combination, some multiplication factor for z1, and then the addition by the mean of x. Okay, this is the standard formula. So mean and the standard deviation of x and x1 are shown explicitly in the 3.72 and 73, and the covariance of random variable x1, x2 is calculated directly using 3.38. So we can try to write here covariance x1, x2 is equal to x1, what you call, and that will become E of x1 minus mu x1, x2 minus mu x2. And if you just try to put the long form of that, right, then we'll get it as sigma x1, sigma x2, E of z1, z2. And this is, nothing but the value of rho z, sigma x1, sigma x2, and rho z, because this quantity is equal to rho z, which we have found in the last class like this. Okay. So having found that, then we see that the transformations 3.72 and 73 leave the correlation coefficient unchanged. So rho of x1, x2 is equal to rho of z. If a different correlation coefficient is required, then the more general transformation for 3.46 and 3.47 are necessary. Then we come to the independence and uncorrelated Gaussian random variables. If we say that the Z1 and Z2 are uncorrelated, then you can separate this out. The PDF can be separated out. And because they are uncorrelated, the value of the correlation coefficient will be equal to 0. And we can write this as like this by separating them. So using 3.65 and 67, we have f of z1, z2, z1, comma z2 is equal to f of z1 into z1, f of z2 into z2, z2. So that means you're just separating out the PDF for z1 and z2, and if you multiply that, then that will get as the PDF of the bivariate random variable. In other words, if a bivariate Gaussian random variables are uncorrelated, they are also independent. This remarkable result is an exception to the general case discussed in the earlier section. So further, there is no need to restrict this result to bivariate case. It can be extended to n Gaussian random variables xi, where I is equal to n, and are jointly correlated, and they are also independent. This leads to the relationship for an n-dimensional Gaussian PDF and CDF, which is something like this. This is PDF, and this is CDF. So these multivariate results for jointly uncorrelated Gaussian random variable turn out to be quite useful in some future applications. So let us take an example corresponding to this. So verify that E of Z1 equal to 0 or E of Z2 equal to 0 as stipulated in 3.68 using the bivariate 3.63. Okay, so using the bivariate 3.63, we need to find the 3.68, that is this. Okay. So using 3.17, Ez1 is equal to integral of minus infinity z1 integral minus infinity f of z1, z2, z1 comma z2, dz1 and dz2. So if you write for all this, this turns out to be the value equal to 1. This turns out to be the value which is a single integral like that. So this turns out to the value, you have z1 here, so therefore dz1 there, and this is dz2. So therefore, if you integrate this with respect to dz2, then you'll get f of z1, right? F of z1, and that is what is written here. Okay, dz1 is as it is there. This whole thing with dz2 will give f of z1. Then using 3.65 and 3.54, Ez1 is equal to 1 by 2 pi integral of minus infinity z1 to the power of minus z1 squared by 2 dz1. So the formula for this is whatever we have written there. That is integral of e to the power of minus z1 squared by 2. Okay. Right? So that's what we'll write. And 1 by 2 pi is always there. So, and that turns out to be the value which is 0. So a similar process shows that E of Z2 will also be equal to 0. So with this, we come to the end of this particular lecture 4. If you have any doubts, again, you can ask. Otherwise, we'll stop at this. So I'll stop the recording.